sign-in sheet for students.
Good afternoon and welcome to the Portland State University Center for Transportation Studies seminar series. And today we're very pleased to welcome Yonnel Gardes from the Transpo group. And Yonnel is going to be talking about the application of microsimulation tools to large freeway-arterial corridors. Yonnel, welcome.
Some projects that I've done as a researcher with the University of California at Berkeley. I was just joining Transpo at the beginning of this year. I worked for 3 years with the California PATH program, and most of the work that I'll be presenting today is based on this. So I'm going to start with an outline of this presentation. What I'd like to do today is to talk about the role of microsimulation in the context of large freeway corridor projects. And I'm going to try to describe a typical approach that we've been using for microsimulation of large corridors. And then I'm going to go through a number of project examples to illustrate some of these applications in different areas. The first area of research or application is the study of HOV, lane operations, or RAM metering strategies, basically traffic management strategies. The second type of applications that I'll be presenting has to do with pavement rehabilitation projects and how to use microsimulation in the context of construction planning. And finally, I'll talk about some project applications that we've done in the area of Homeland security, which is another potential area for using microsimulation. But first, I want to start with a general introduction about what is microsimulation and what it is useful for. Microsimulation can help in a number of ways when dealing with the study of large freeway corridors, because it allows for analyzing some very complex network vehicle interactions at the corridor level, which is really hard to do with other methods. It can also help test the capacity of the bottlenecks and analyze and compare some design treatments. We can also evaluate the benefits of ITS systems and services, and this is an area for which simulation is very useful and very often used. The nice thing about simulation is that we can look at the interactions of different modes of transportation. For instance, on when dealing with large corridors, we can look at HOV operations, bus operations, light rail, freight, and how the combination of these modes interact and trying to design some operational strategies that are optimized for all modes of transportation. Then another very important area is the analysis of work zone and the traffic impacts related to construction or rehabilitation work. And microsimulation can help in the process of developing traffic management strategies and traffic mitigation strategies. And last item that I've listed here is that pointing out that the microsimulation can be very useful in terms of presenting technical results, visualization and communication supporting tools is something that is really important when talking about microsimulation. This slide lists a number of typical steps that you're going to have to go through when applying microsimulation to pretty much any type of applications. This is like a constant that comes back for any projects. First, there's going to be a data collection step. And I'm going to go through each of these steps later on. So this is just the general process that is going to be followed. Then there's the network building process. There's the demand estimation process, the model calibration and validation, then design of experiment, then the run of the alternative scenarios, gathering statistics, and visualize animation, produce outputs. I'm going to go through each of these steps to illustrate what is meant there. In terms of data collection, usually we start with a data list of data requirements. What are the data that are going to be needed to build a microsimulation application? And I like to classify the data into these 4 broad categories. Some of them have to do with the supply information, basically the geometric characteristics of the network. Then there's everything that has to do with the control, like traffic signal timing, so RAM metering rates on freeways. Then there's the demand side of the simulation, which is coming up with an origin-destination trip table, or most of the time, because we're dealing with dynamic modeling, we want to come up with a series of OD tables that can be 15-minute OD tables or 30 minutes OD tables, so as to capture the variation of demand over time. Counts are important for the demand estimation process and also for the validation and calibration process. Counts, flows, speed measurements, usually under the form of TAC runs or travel time based on floating car studies, are very important to calibrate and validate the model, making sure that the model is able to replicate existing traffic conditions before looking at any potential alternative scenarios. Delay congestion information is also important to calibrate the model. Just a few slides now to illustrate some of the data that we've been using on freeway simulation projects. This is a slide that shows the total travel time to cross an entire freeway section that we've been studying at different days during the week. You're basically computing the travel times taken to cross the freeway corridor. And that's some data that's going to be useful in calibrating the model. When we have access to TAC run or floating car studies information, what we like to do is to display the information on this type of time-space diagrams that actually show the speed at given sections along the freeway, average speeds on 15-minute time intervals. And by using different colors on this matrix, you can pretty easily see, the congestion pattern, where and when the congestion is occurring on the freeway. And again, that's very useful in terms of calibrating and validating the model. Intersection counts, again, that's important for the demand estimation and for the validation process, whether at the intersection or on the freeway itself. These are some examples of data that were collected from the PEMS, the Performance Measurement System. It's basically the loops that are available on the California freeways. Now, once we have all this data, we can start actually building the model. And the first step is in the network building is to basically get some good geometrical information. And these microsimulation models that I'm talking about today, that are tools like Paramix, vSim, CoreSim integration, they provide really high quality graphics the visualization is really powerful, but that also means that you need some high quality inputs to go into your model, so that you really matching real life conditions. And in terms of how we build these models, typically the process is to use either aerial photos or CAD drawings that are actually imported into the traffic simulation software as a background layer, and then you can build your nodes and links on top of this background layer. So that's a very helpful and quite efficient way of building models. Even large models can be built, relatively quickly and with a lot of high level of accuracy using these techniques. There's also another way of doing it is to convert GIS files into a microsimulation model, and that's an option that we've been investigating on some of the projects that I worked on in California, and I'm gonna show you this a little bit later in the presentation. This is an example of a network that we've been working on as part of a freeway pavement rehabilitation project. But as you can see, this is in the Long Beach area, Southern California. And you can see that it's a pretty large network that, we're talking about maybe 15 miles by 15 miles network size. And you can see the aerial photo in the background that was used to actually build the Paramix, in this case a Paramix network, on top of this aerial background. And then the interchanges details. You can see an example here of a pretty complex interchange that was modeled, and the idea is to replicate the actual geometry as closely as possible. That's another network, like of pretty large size, that we've built on the 580 Freeway-Arterial corridor project. Again, that was done using aerial photos to get the geometry of this network. Like I said, there's also the option of using some GIS conversion tools. We actually were involved in a project to develop a conversion tool from ArcView to Paramix, and we've tested and used this conversion tool on some network building applications, and that's pretty powerful. It doesn't give you a perfect network, but it's a really good first sketch network that can later be refined. But when dealing with large networks, because GIS files are usually easily available, it's a very quick and efficient way to build a first sketch network. Now, once the network is built, like the second main area of model inputs has to do with the demand. And like I said, what we want to do is to compute or to come up with OD trip tables. And usually, one way of doing this is to start with a pattern OD.
For some folks may not know what OD is. So.
Yeah, origin destination. Basically, it's like the network has some zones that are going to be generating and attracting traffic, and the way the vehicles are loaded into the network is based on the origin destination trip table that is going to be assigned on the network. And like I said, estimating these OD tables is is a process that can be rather complex, but one way of doing this is to start with actual counts and then using a synthetic OD estimation technique to reconstitute the OD table based on the actual counts. So that's the process that is described here in general terms. I could go into more details if you're interested, but typically one of the inputs of this estimation technique is a pattern OD, which is typically developed as part of a planning exercise. So it's a 4-stage model that is used to develop the first planning OD matrix, and this is the one that is going to be refined using actual counts collected on the network. Once we have these two basic sets of information, the network supply side and the demand side, then we're ready to actually load the network and see how it performs in comparison with actual traffic conditions. And this step is called calibration, and basically the goal is to adjust the model so that it most accurately replicate existing traffic conditions. And typically this process involves checks and revisions in a number of parameters that I've listed in there. Some of them have to do with the general simulation configuration parameters. You can also revisit the network geometry as part of the calibration process. You can check and modify your demand information. Driver behavior characteristics is another area to consider. And finally, routing strategies are very important in terms of calibrating the model. Yes, question?
The general configuration parameters, how do you account for physiographic conditions, visibility, weather, road conditions?
Not directly. I mean, there are ways to approach this type of situations, but typically by general simulation configuration, what I mean is the number of time steps per second, the average headway factors between the vehicles that are going to govern the car following and lane changing model characteristics. These are the types of general simulation configuration parameters that we can consider at this stage. One thing that is typically done in terms of validating the model is to compare the speed contour map that I've introduced before, the one that's reflecting existing traffic conditions, with the one that is derived from the model outputs. And that's an example here on this slide. On the top part of the slide shows the field conditions, and the bottom one shows the speed contour map predicted by the simulation model. And you can see that the match is pretty good. This is what you want to make sure is that your model is able to replicate congestion conditions, when and where they occur in the field. Another way of checking the model is to compare the counts, again, from the field and from the simulation model. And that's an example at one particular freeway location. You can see the pattern of counts over time from the field and from the model. Now that I've presented some general characteristics of microsimulation projects, I'm going to walk through a number of project applications. And like I said, I've classify these projects into broad application areas. And first, I'm gonna be talking about applications in RAM metering or HOV studies. And I've been personally involved in 3 projects of these types, 2 in the Bay Area, working for the California DOT, Caltrans, and 1 more recently in the Seattle area. The first project example is the I-680 freeway corridor, and it's a pretty long corridor that's illustrated here, about 19 miles long. We looked at the southbound freeway direction only. This is what we were concerned about as part of this project. And the idea was to simulate the potential impact of adding an HOV lane and implementing RAM metering at each on-ramps along this network. This is the most congested freeway section in the Bay Area. A lot of people commuting south to the Silicon Valley, San Jose area, and living way far north where they can afford to live. And that's creating a lot of congestion. That's a 3-lane freeway facility, and there's very little alternate routes or public transportation that could be considered. So it's very congested, and there's really a need for improving traffic conditions on this freeway segment. What we did is that we simulated this with panoramics, and we looked at a number of different alternatives in terms of implementing this HOV lane and these RAM metering strategies. We looked at these strategies independently or in combination, and I have a few slides to illustrate some of the results of this project. This is showing you the effect of adding an HOV lane. Basically, on top you have the existing traffic conditions, and at the bottom you have the congestion pattern with the added HOV lane. So you can see that you don't get rid of the congestion, but you certainly make things a lot better. One thing that's interesting, yes, question?
Yes. What happens between section 30 and 31 that causes the abrupt speed change? Is that like another freeway that everyone gets off to?
Yeah, that's the main bottleneck. That's a non-ramp with a lot of traffic merging into the freeway. That's creating a major bottleneck.
Then downstream of the merge, the flow is pretty good.
Yeah.
Thanks.
What are the red speeds?
Speeds below 35 miles per hour on average over 15 minutes time periods. And orange is between 35 and 50.
Actually, the cutoff is 40 between orange and red.
Yes.
39 and 38 are red.
Yeah, so it's below 40. Yeah. This is showing you like one thing that we can do in simulation is to look at the performances of different types of vehicles, and in this case we were interested in the impacts of the HOV lane on the carpool vehicles versus the vehicles using the general purpose lanes. And also the effect of adding the HOV lane in general. So on top you have the average freeway trip times before the introduction of the HOV lane, and the 2 curves at the bottom are showing the performance after the introduction of the HOV lane. So what you can see is that everybody benefits from the introduction of the HOV lane, whether or not you're actually using it. The HOV vehicles that are eligible and that are using the HOV lane benefit the most. But even the single occupancy vehicles that are using the other lanes also benefit from the creation of the HOV lane. Questions?
Yeah, I was wondering, when you run the model with the HOV lane in it, where do you get the configuration parameters for the HOV lane? How is that, since it's an assumed lane, since it's non-existent, how can you decide what the parameters are for that lane and how it'll affect?
What kind of parameters? You mean the geometrics or the one thing that's very important is whether you allow vehicles with 2 passengers or 3 passengers. That's something that is not decided at the time you do the simulation. So, one thing that's interesting is to look at the different scenarios, and look at the relative benefits of different scenarios. Also, another important aspect is how do you want to restrict the use of the HOV lanes only during peak times or not? In California, usually the HOV lanes are restricted to HOV vehicles only during peak periods on weekdays. And in Seattle, for instance, it's different. It's always restricted, to HOV vehicles. So that's something that's really interesting in testing in simulation. You can really look at different scenarios and get a better understanding of how these things affect the actual performances of your system.
Well, I guess I was just wondering, are there basic assumptions made about the HOV lane, such as use? And if these assumptions are made, does it come from prior studies of other HOV lanes?
Yes, yeah. But like in this case, for instance, this HOV lane that we're talking about is in the design stage. So we have some ideas about how it's going to be built already. But just north of the section that was under study, there was an existing HOV lane for which we could get information about the actual use of the HOV lane, and that's something that we used for our model. Yes?
Is the travel time based on per passenger or per vehicle? And is this assuming and adding a lane? And so the base no HOV doesn't consider adding a general purpose lane?
Yeah, you're right. I mean, in this case, we're talking about passenger vehicles, but when you looked at the overall performance of the system, in simulation, you can do both. I mean, you can look at passenger vehicles, passenger hours versus vehicle hours, and using some assumptions about average occupancies of the different vehicle types. Yes. Yes, question.
I don't think you quite answered one of his questions, where on your base with no HOV, are you comparing, let's say if you had a 4-lane road before and you've added one, and so for the HOV lane, are you comparing a 5-lane for the base and then a 5-lane for the HOV, or are you still back to comparing just the 4-lane without the additional lane that you're adding for the HOV?
Well, that's certainly something that we could have done. Yes, that's not that. I don't have the results of this run because I don't think we've done it, but that's something that could have been done. Once we have the model, you can really have a lot of flexibility in terms of looking at different scenarios, and what if this added lane is a general purpose lane as opposed to an HOV lane? What if it's open to only 2+ vehicles or 3+ vehicles? It's really the nice thing about simulation is that once you have a calibrated network, then it's really easy to run a wide range of scenarios and look at the relative benefits of all configurations.
So I think I heard the answer.
I think I heard the answer.
Could I say something?
Just to clarify, having lived in California for a long time, in California the only way to create an HOV lane is to add it physically. That there's a state policy they will not convert an existing lane to HOV. I suppose that could change in the future, but maybe that's a good piece of information to have. Our HOV lane here in Portland was not added. It was converted from mixed flow to HOV, but in California they never do that.
So this graph is added lane, HOV, and then his other question was whether the plots are by passenger or by vehicle. So this plot, is it by passenger or by vehicle?
Yes.
There's two choices there. Either is
This
by
is
vehicle.
this is vehicles.
Okay.
Yeah. What I'm showing you here is the setup, the ramp setup for RAM metering with HOV bypass. And like I said, we wanted to look at the combination of HOV lane and RAM metering. And this is to illustrate the results in terms of mainline delays. What are the gains on the main line of introducing the metering scenario? And we have delay contour maps, similar to the speed contour maps that we've shown before. Delays in vehicle hours. So basically, the delay is defined by the travel when the speed is below 35 miles per hour. The additional travel time is computed in vehicle hours for each mainline section. And what we can see here is that the overall delay on the main line has decreased by 36% with the introduction of the RAM metering system. Yes, question?
Do you add vehicles on the freeway for the metering on? Because when you turn the RAM metering off, on, a lot of
Press the
vehicles.
button so the red light shows up. It says press.
So when you turn the metering on, doesn't that divert a lot of traffic from the freeway? Then when you turn it on, are you adding additional trips to the freeway?
Additional vehicles? No. No, it's the demand is assumed to be kept constant. One way of looking at the RAM metering scenario also is to not only look at what happens on the main line, but also on the ramps. And obviously, when you turn the metering on, you increase your delays on the ramps. The question is whether or not your gain once you enter the freeway is good enough to actually improve your overall travel time. And obviously it's going to depend on how much time you spend on the mainline freeway as opposed to on the ramps. And what we did is that we looked at the comparison of travel times depending on when you enter the freeway, before and after the metering. And what you can see is that on the left side of this graph, these are the vehicles that are traveling the longest distances on the freeway. And because of that, the scenario with RAM metering is consistently better than without RAM metering. The opposite is true on the right side of the curve for shorter distances, because you spend additional times on the ramps and not so much gain on the freeway, then your overall travel time tend to increase in some cases. So this is really an interesting type of analysis in terms of equity issues related to RAM metering. And again, it's interesting to look at different scenarios in terms of how you control your ramps, what kind of algorithm you use, whether you use fixed time metering rates or real time adjusted metering rates is an important criteria in terms of the overall performance of the system. Just to show you a little visual animation here, that's another network, another corridor that I've worked on, the 580 corridor. And again, on this we looked at HOV, RAM metering, and combination of these two. This network didn't have only the freeway, but also a number of surface streets, and we had a total of about 100 signalized intersections on this network. The other example that I wanted to use as an illustration is a recent project, actually a project that is going on right now as part of in Seattle, as part of the 520 bridge replacement and HOV lane project. We looked at different scenarios in terms of freeway and surface street treatment in one particular alternative that is in the design phase right now. What we looked at a particular freeway exit and the intersection at the end of the freeway exit that was found to have a tremendous impact on the overall performance of this area. And what we did is that we simulated this interchange, trying to capture the demand as predicted for year 2030. And we simulated different treatments for that particular intersection. We looked at signal controls with different timings, and we looked at an option with no signal control and free merging onto the surface street. And we looked at the queuing patterns for different scenarios. We looked at speed patterns, not only on the freeway but also on the surface street. And that's something that is very useful for the neighbors that are obviously concerned by this project that is going to have a huge impact on the area. And looking at different scenarios, how you treat not only the freeway but the adjacent surface streets using simulation is very useful for this process. Now I want to switch to another. Yes, there's a question.
I'm just curious to know what is the difference of using an adaptive RAM meter and if you're using a pre-time on your simulation model with relation to speed or trip time.
I'm sorry, I can hear you.
What is the difference of using an adaptive RAM metering and a pre-timed RAM metering in your simulation model? What are the effects if you use either of the ones? Is there any difference?
Yeah, there is a difference, depending on how you treat the intersection, depending on how you control your signals. There's obviously a difference in terms of how the system performs. Yeah. Another type of important application of simulation is in conjunction with pavement rehabilitation projects, and I'm going to be talking about this in relation with two projects that I've been involved in Southern California. Why do we need to do traffic analysis or microsimulation for construction planning? Well, it's very important because it can be very useful in terms of staging the different phases of the construction work and looking at the actual impacts in terms of delays that are going to be created by the construction work, looking at different scenarios in terms of when and where you do the work, and looking at their comparing the different scenarios in terms of actual delays experienced by the traveling public. You can analyze system-wide impacts, looking at not only the freeway but also the parallel arterials that are going to be impacted by the construction work. What's important is to help design the traffic management plan, analyze the potential impact of diversion from the freeway to the surface streets, and also help support the public awareness campaign in conjunction with these projects. Well, traffic modeling can be a very helpful tool to help you do all this. What is required? A good travel behavior model, a traffic flow simulator to capture the impacts of the lane closures due to construction, and not only the impacts but also how people are going to react in front of these unusual conditions. Whether they have information before, during the trip, how is the system going to perform under different scenarios. Simulation can also be used to evaluate the potential impacts of different traffic mitigation strategies like signal retiming, traveler information, RAM metering, lane widening, media campaign. All these mitigation strategies can be studied with the simulation model. Diversion is obviously a very important concern. Is it possible, feasible? How do you actually control the diversion patterns? What kind of information, what kind of messages can be used, and how? What we developed through these two projects that I was talking about, we tried to develop the concept of integrating constructability and traffic analysis, and looking at the interactions of these two. Typically, constructability is not really concerned about traffic impact. So what we wanted to do is to add the traffic impact component into the constructability analysis that is most traditionally done. And what we did in order to do this is that we actually did a traffic monitoring study of some actual work that was done on the I-710 in Long Beach, and we actually measured the impact on traffic conditions of this construction work. And we use this data to calibrate and validate a simulation model. We looked at different phases before, during, and after construction, and all this data that was collected was really helpful in terms of understanding how travelers behave in relation with the construction work. These are different devices that were used as part of the traffic monitoring study. Pretty much all available devices were used at different. In the center of the graphics, you can see the construction zone, but the network that we looked at was obviously much larger, so that we could capture the effect of diversion. The freeway was never totally closed, but only some lanes were closed. But we knew, and the local agencies knew, that this type of work was going to generate a lot of diversion and additional traffic on the surface streets and also on other freeways in the vicinity. Once we had all this data, we were able to use the simulation tool to run some additional scenarios and also help design the future traffic management plan. The work on this particular project, the work was done on weekends, so they would actually close the freeway on weekends so that they can accelerate the work and deliver the final product quickly. On this particular project, the decision on doing the work on weekends, totally closing the freeway, was already done when we came on board for the simulation study. But on some other projects, when we are involved at an earlier stage, we can actually help deciding when to do the lane closures. Whether it's better to do it on weekends or at night or on weekdays. During certain hours, we can really compare the different scenarios in terms of their impact on the traffic conditions and how they compare in terms of traffic impacts. The sensitivity analysis that we did was to look at things like with or without traveler information systems. We looked at the learning process from one weekend to the next. We looked at weekend versus weekday night closures, and the effect of passenger cars versus trucks was also of concern. These are some examples of measures of effectiveness of statistics that you can look at as an output of the simulation. Can look at overall network performances or route by route, and some detailed measures of effectiveness. I'm going to move quickly on this so that I can get to the last application area. Again, this is showing you the flows before and during construction. During construction, we have two graphics at the bottom. The flows estimated and observed, and you can see that the model was actually able to pretty well capture the actual flows that were observed in the field. Capacity estimates also as observed in the field versus predicted by the simulation. Just run this so that you have a better idea. That's the second pavement rehabilitation project in San Bernardino. What you can see here is you can look at the freeway. You can see that one side of the freeway is actually closed in this case, and the traffic is moving in the two directions on the other side of the freeway, and we have 2 lanes open for both directions, as opposed to 3 lanes before. And as part, this project was different from the I-710 Long Beach in the sense that we were involved earlier on in the process, and we could really help with the comparison of the different construction scenarios, whether to work on weekends or at nights, or closing the freeway totally or closing just one side, closing lanes or ramps. We looked at a number of different scenarios, and we were really able to to help the decision makers in the process of choosing how this construction was going to be performed. I'm going to go quickly on this because I'm going to run out of time. I'd like to talk about another type of application that I think is very, very interesting, very promising, is that to use simulation in the context of Homeland Security. And what we were involved in a project funded by the Department of Homeland Security, and we at UC Berkeley, we worked as a subcontractor to the Lawrence Livermore National Laboratory. They were in the process of developing a radiation detection system that would be installed along the freeway. And what we did is we helped them with the development of the concept of operation for this radiation detection system. And basically we wanted to help them illustrate how this system would work, so that they could go and talk to the local stakeholders and have an actual visualization of the network and the detection stations, and how the process of detecting and tracking the vehicles would actually be done. And the network that we looked at is about 50 miles long, and it's just the New Jersey Turnpike, I-95, south of New York. And the network that we coded was actually just south of the Homeland Tunnel. And the idea was to try to identify potentially dangerous vehicles, track them down as they progress through the Homeland Tunnel, and then intercept them just before they enter the tunnel. I'm going to pass quickly on this. This is to show you the network that was coded. We coded all the interchanges, toll stations, as this is a toll road freeway. This is showing some details of interchange coding. These are the toll stations that are numbered on this graph along the freeway. This is what we did as part of this project. The idea was to simulate the process of detecting the vehicles, tracking them, trying to predict their travel time to reach certain points along the network, and then the interception process. And we had 4 stations along this 50-mile freeway segment. Starting from the south, this is where we first identify suspect vehicles. And the idea is that when the simulation is running, you would actually see these particular vehicles being highlighted, and there would be a picture of this vehicle being taken at the detection station. And what we would do is to predict the travel time to reach various points along the network. So we're going to first identify the vehicle as a suspect at station 4 here to the south, and then predict his arrival time at station 3, station 2, and station 1. And this is really going to be very helpful in terms of reacting to this detection event, and how you plan the reaction and finally the interception of the vehicle. Because this radiation detection system may be prone to false alarms, it's important to confirm the status of the vehicles as it passes through different stations. This is why we have 4 stations along this network. So at station 3, basically, if the alarm is confirmed, the status of the vehicle is going to change from suspect to presumptive At station 2, it's the status it becomes confirmed, and finally at station 1, this is where the interception is taking place, supposing that the alarms has been confirmed all the way through. And what this project involved was a customization of the base Paramix network, Paramix software, so that it could actually replicate all this process. And what we did is that we used some new APIs or application programming interfaces that we coded to actually replicate the radiation detection system and the different phases that I just went through. This is like a screen capture of the target vehicle that you can see at the bottom right that has just passed the first station, and because this vehicle has been identified as a target vehicle, his status has been switched to suspect, and you can see a picture of this vehicle being taken, and also in this window here, reporter window, you can see not only the vehicle status currently, but also his predicted arrival time at the subsequent stations along the network. This is when this same vehicle reaches station 3. Again, his status is updated to presumptive, and his estimated arrival times at the next 2 stations is also updated. Same thing at station 2, and finally the interception at station 1. This is just showing you that our travel time prediction algorithm, how the actual travel time arrival compare with our range of predicted arrival time. And this is showing you the red arrows shows the actual arrival time, actually always being within the range of the predictions. These are some conclusions based on this particular project. We thought we illustrated the fact that microsimulation is a really powerful tool to visualize how this system would perform, and this was actually very helpful to illustrate the concept. And Paramix was flexible enough to be customized to actually replicate this particular system, even though it was not originally developed to do this. But because of this application programming interface, you can do a lot in terms of adding some new functionalities and functions, specific functions that you want to simulate, and hook them up with the actual traffic simulation standard software. Yeah, there's a question?
Yes, under that system, if you've had an idea that there's this radiation, emitting vehicle all the way since Philadelphia, why wait all the way to Jersey City to do the interception? I mean, it seems to me like if you had, say, a nuclear bomb in a truck, by the time you get to the spur off the main turnpike to the tunnel, you're already within the blast radius of Lower Manhattan. So why not put them closer together and then, say, intercept him where he's still in the suburbs?
Yeah, that's a good question. I mean, what we did here is that we looked at one particular scenario, but obviously what you're describing is something that would be helpful to look at. One thing that was a concern for the people that are working on this actual radiation detection was the rate of false alarms. They were very concerned about activating a process that could actually not be necessary because of the potentially high rate of false alarms. So they really wanted to have this capability of confirming at various points before actually doing the interception. But that's, again, that's not a system that's implemented. That's just a feasibility study, and we use this to help them communicate basically and visualize how this could work. But you're right. I mean, why? If you have a good level of confidence in your system, you don't want to wait 50 miles until you actually intercept the vehicles. Yes. Yes.
That's your construction application. How much did you?
Or public information mitigation, how well did that show up in the simulation? How could you model how much impact it had on the traffic flow?
Your questions about
the public outreach mitigation,
public outreach,
construction, and how,
well, it's obviously difficult to capture the impact of public outreach in the simulation. But one thing that we did is that we, well, first, the traffic monitoring study that we did on an actual construction project helped us with calibrating the model for other applications, because by actually doing this very detailed data collection on that particular project before, during, and after construction, we were able to gather a really good data set to help us capture some of the effects of public outreach. For instance, the vehicles that cancel their trips or the vehicles that use other routes, you can partially get a handle of this, if you have a really good data set to work with. Typically, it is assumed that because of construction, you can have 5 or 10% of vehicles that are actually even decided not to show up at all, not to do the trip at all. You can have also effects in terms of changing modes, changing travel times, changing departure times, changing modes, changing routes. This is obviously very difficult to capture, but we can make some reasonable assumptions based on actual observations on ongoing projects. Yeah.
Unfortunately, our time is up for today. It's past 1 o'clock. I'm sure Yonnel will stick around for a few minutes. I'd like to thank Yonnel for joining us. I think there might also be some people who are graduating in June who might want to talk to you about whether your firm is hiring. But before we officially thank Yonnel, I'd like to mention that next Friday, Bob Hadlow, who's the historian for the Oregon Department of Transportation, will be talking to us about the historic Columbia River Highway. So let's thank our speaker. Thank you.
You have some questions?